All right, everyone, welcome to the third video in our MathByte series on vectors. Before we get started, I just wanted to let you know that I kind of got burned out doing lots of video editing, and so what I'm going to try to do is save myself a little bit of work and put out some more videos per week, just by talking kind of a little bit more off the cuff. What that means is I won't be reading off a script, and so there might be a little bit more kind of like ums and ahs while I try to think through sentences, but hopefully, you'll bear with me, and hopefully this also makes things kind of feel a little bit more sincere and personal as well. In any case, in this video, what we're going to do is try to start understanding how we can talk about vectors algebraically, or in other words, without having to use a picture, right? Before, we talked a lot about using graphical descriptions of vectors, and then like if we needed to add two vectors together, we could do that graphically. And then if we really wanted to know what the kind of resultant vector of a vector addition looked like, we'd have to like measure it and then describe it, describe the measurements, right? We'd have to like physically use a ruler or something. And that's kind of inconvenient for physics problems, right? Because the goal is to be able to like algebraically compute stuff, so we don't need to break out the ruler every time we need to like combine forces to find the total force on some object. And so in this video, the kind of main question we're going to answer is how do we express vectors algebraically, or in other words, without having to use a picture. And so when we started the discussion on vectors, we claimed that vectors are fully defined by two numbers, a magnitude and a direction, right? So why don't we just use those to express what our vector looks like? So what I have here is like this purple vector A, and this purple vector A has a length of about 2 centimeters and makes an angle 45 degrees relative to the x-axis. And so one idea we can have is just, what if we just tell the reader what this is by telling them that it's 2 centimeters long and makes an angle of 45 degrees like this? Well, it turns out this is actually a way of describing vectors called the polar coordinate representation. The reason this is called the polar coordinate representation is really just because we're using polar coordinates like in Algebra 2 to describe this vector, right? We're basically directly able to read off what the magnitude is, and that's this first number here, and we know what the direction is. And if we think back to Algebra 2, right, any position r can be given by some distance r and an angle theta. And so this mirrors kind of exactly what we do in Algebra 2 when we're using our polar coordinate representation of like points on a graph as well. The downside of using this in physics is even though it's really easy to just kind of read one of these vectors in polar coordinates and figure out what it looks like, it turns out it's really hard to add vectors this way. So let's look at a quick example problem that shows kind of why it's really difficult to use polar coordinates to add vectors. So take this vector A we had before, and let's add a new vector B and try to compute vector C as the sum of vector A and vector B. So we're going to add these two vectors up and try to figure out what the resultant vector is. Fortunately, I've kind of put B already on the end of A, right? And so I've done basically half of the addition problem already. But graphically, right, the idea is we know that if we add vector A and vector B, then the resultant vector, vector C, is going to start where the first vector starts, and it's going to end where kind of this like vector chain ends up. And so our vector C graphically is going to look something like this, right? And so we can kind of make a guess that it's going to be somewhere a little bit like in the neighborhood of being a little bit longer than A and B, and it's going to have an angle of like 60-ish degrees relative to the x-axis, or something like that. It's definitely between 0 and 90 degrees, right? And so the question is, well, what happens if we want to algebraically add these together, right? Can I express the vector C in polar coordinates by just using vectors A and B? And so one kind of initial guess we can make is, what if we just add the magnitudes together and we add the directions together? In other words, I know vector A has a length of 2 and vector B has a length of 1, so maybe C has just a length of 3 centimeters. Similarly, because A is at 45 degrees and B is at 90 degrees, well, maybe C is just at 135 degrees, right? And so the idea is if I draw this vector that we came up with, that we're not like 100% sure about, then maybe it turns out to be the correct vector, right? So if I take a look at this vector and I draw a vector that's about length 3 centimeters at 135 degrees, well, I'm going to draw this one in green because it's completely wrong, and we'll see that in a second, right? But that's going to look something like this. And so we can see this green vector, which is our kind of guess for the algebraic addition, is definitely not in the right ballpark compared to our graphical addition, right? And so what we find is that it'll be a little bit more complicated than just kind of smashing together the magnitudes and directions if we want to try to add vectors up in the polar coordinate representation. And so what that means is polar coordinates are really, really awful to try to do vector addition in. There's no kind of obvious easy way to do this. And this is really the major downside of using polar coordinates. Even though it's really easy to kind of read a polar coordinate representation of a vector, doing arithmetic in polar coordinates is not so simple. Fortunately, there's another representation of vectors that makes vector arithmetic much easier. And let's talk about that now. And so let's start with this new vector, vector A, and I made it a little bit longer, but it's a 5 centimeter long vector at 45 degrees counterclockwise from the y-axis. So I can label this. It's about 5 centimeters long and kind of at like a 45-degree angle here, right? And so what we can see is that if I draw these little auxiliary lines here, a dotted line kind of going down to the x-axis, and to the y-axis as well, I can see that this vector extends kind of 3.5 centimeters to the right and 3.5 centimeters upwards, right? And so one idea we might have is just to express this vector by telling someone how far it extends in the x and y directions. In other words, I kind of talk about this in the same way that we plot points on a graph, right? I just give you the x and y coordinates. And so in this way, we can talk about the x coordinate as being 3.5 centimeters. And we can write down the y-coordinate as well as being 3.5 centimeters. This is called the rectangular coordinate representation. Rectangular coordinates. And so this representation is nice because it makes it really explicit how far the vector sticks out in different directions, right? Each of these numbers in this ordered pair is called a component of the vector because it kind of partially describes something about the vector. This first number here is called the x component, and I'll abbreviate it here as x comp. And the second number in this ordered pair is the y component. And the idea is I can just tell you how far the vector sticks out in the x direction and the y directions, and you can put these two components together in order to form the full vector. In other words, I can kind of draw out the x component like so, and I can draw out the y component like so, and we see that by giving these two components, we can construct the full vector, kind of with a vector sum, right? Another important thing about the rectangular representation of vectors is that these vector components have to be given in terms of something called a basis. The usual basis we're going to work with is called the Cartesian basis, named after the guy who invented graphing, right? Like in our Cartesian plane, we're using Cartesian coordinates. And so what that means is the numbers that we give for the x and y components are based off an idea or some convention for what counts as positive and what counts as negative. I like to draw this little cartoon to remind myself that in the Cartesian basis, any number that's positive means that the thing sticks out to the right or upwards, and anything that's negative sticks out to the left or downwards, depending on if I'm talking about the x or y components. This little cartoon kind of cross with the pluses and minuses is a good thing to start drawing every time you need to do a problem with vectors, just to remind yourself to be careful about kind of positives and negatives here. And so this is really nice. We have another way to express vectors by giving the x and y components that tell us how far the vector sticks out in the x and y directions. Generally speaking, what this means is a vector can be expressed by its components like so. And so in this form, right, we can just read off these components, draw them on our Cartesian plane, and then figure out what the vector looks like by doing the vector sum, kind of like what we've done here on the left-hand side. Okay, so let's take a moment here and do a couple practice problems just to kind of solidify some of these ideas for the rectangular coordinates. And so what I've done here is I've written down a vector u with components like so, where the x component of u is 3 centimeters and the y component of u is 4 centimeters. And what I'd like you to do is take a second here and pause and just try to draw out the components and then use the components to draw the vector u. And so go ahead and grab a sheet of paper and pause here for a minute and see if you can draw the vector u based on the components I've given. Okay, let's go through this together, right? So let's start by reminding ourselves that the vector components are based on the Cartesian basis, which treats the right and up as positive values, and vector components that have negative values go to the left and downwards, right? And so we can start by looking at the x component here, right? And we see the x component of u is positive 3 centimeters. And so based on our basis, right, we know that the vector u must extend 3 centimeters to the right, like this. Then we can look at the y component, and we see that the y component of vector u is 4 centimeters, and so we know that the y component looks something like this, right? Since it's positive, we know it sticks up. And so the vector sum of these two things here, I can compute by taking this y component, and I can kind of move it over so that it starts where the red x component ends. And the total vector u must then look something like this, right? It starts from the origin here and ends up where our second vector ends. And so the vector sum of these two components gives me what vector u looks like. And so hopefully that's kind of what you came up with here. Okay, let's do another quick practice problem before I let you all go. And now what we have is a new vector v in component form, but we now have a negative x component, right? So let's just get some practice doing a problem where we have a negative component. So once again, go ahead and take a minute, pause here, and try to draw out these components and then add them together to figure out what the total vector v looks like. Okay, let's work through this problem together now. So once again, the first thing that I'm going to do is draw the little Cartesian basis to remind myself that positive values go to the right and up, and negative values go to the left and down. And so in this case, I have a negative x component, right? And so based on our vector basis, that means our x component points 1 centimeter to the left. And so our x component for this vector, vx, looks something like this. Then I can look at my y component, and I see that the y component points 4 centimeters upwards, right? Because it's a positive value. And so that means my y component looks something like this, and I'll label it vy. And then once again, kind of putting these two together. In this case, I'm going to take vx and kind of slide it up here. I can construct my total vector v by just doing the vector sum of these guys. And so my vector v starts at the origin and ends up over here. And it looks something like this. That's a little bit far off. I'll redraw it to make it a little cleaner looking. Good. And so that's what our vector v looks like with a negative component, right? And so we see the difference here is that vector v, because it has a negative component, points a little bit to the left, right? And so that's why it's kind of in this upper left-hand quadrant rather than the upper right-hand quadrant like before. Okay, hopefully you're kind of noticing a pattern here, right? The rectangular representation of vectors is still pretty good for visualization, even though it doesn't directly give you the magnitude and direction. But because the components tell us about whether the vector points up or down or left or right, and the size of the components kind of gives us a flavor for how vertical or how horizontal the vector is, we can still kind of get an idea of what this vector looks like graphically just by looking at the components. And as we'll find out later, it turns out that doing vector addition and subtraction is really, really easy in rectangular coordinates. And so this will be kind of the general representation of vectors that we'll use mostly for calculations later on when we're doing some problems. Okay, that's really all I have for this video. And so as usual, let's summarize really quick kind of what we talked about. And so we found out that there are two ways to represent vectors. The first one is a polar representation, in which we are kind of directly expressing the vector by telling you what the magnitude and direction are. Usually for the direction, we assume that the kind of reference direction is the x-axis, and we're traveling counterclockwise from that, right? And so for a vector that looks like this, we know this vector has some length r, and we know that this vector makes an angle of theta with respect to the positive x-axis. And so the polar representation of this vector might look something like r equals, and then I'll tell you what the length is by giving you the r here, and I'll tell you what the angle is by giving you this theta. And so these two kind of descriptors give you the exact idea for what this vector looks like, right? And the caveat here, right, is that in polar coordinates, it's hard to add vectors. We saw earlier that when we had two vectors in polar coordinates, you can't just smash the magnitudes and angles together. And so while polar coordinates are really good for kind of directly reading off the magnitude and direction, you don't want to use them if you have to add vectors together. The other kind of representation we talked about was the rectangular coordinate representation. In this representation, what we do is express this vector by telling you what the x and y components are. In other words, I can express this vector by telling you how far it sticks out to the right and how far it sticks up upwards, right? And so to represent this vector, I might say that this vector r is given by the x component rx and the y component ry, like this. And so in this rectangular form, right, the idea is we're just going to express how far this vector sticks out vertically and how far it sticks out horizontally. And so remember that when you express a vector in rectangular coordinates, there's kind of an assumed basis underneath this. Or in other words, you have to kind of do this relative to a particular basis. The usual one that we'll be using in physics is the kind of standard Cartesian basis, in which positive values go to the right and upwards, and negative values go to the left and downwards. There are going to be some exceptions to this. So for example, when we move on to doing problems involving ramps, we'll have to do this kind of goofy thing where we rotate our coordinate basis. Or when we do problems on a pulley, there's going to be kind of this weird scheme that we have to do. But we'll talk about that when it comes up. For now, just remember that the rectangular coordinate representation uses the Cartesian basis, the same one that you use when you make plots, right? The upside of the rectangular coordinate representation, as we'll see in the next couple of videos, is that it makes adding and subtracting vectors and even multiplying vectors much easier. And so this will be the kind of more functionally useful representation of vectors. Okay, that's all I have to say about the algebraic representation of vectors for now. Vectors are a really well-studied and really rich part of mathematics, and the stuff that we went over here is really just meant to be a crash course that gives us enough to kind of do physics, but this is by no means the end-all be-all for vectors. Later on, we'll do some more complicated stuff with vectors, like I alluded to earlier, right? We're going to be doing things like rotating our basis for ramp problems, but let's not worry about that too much for now. In the next video, we're going to dive into how to actually do vector arithmetic, in other words, vector addition, subtraction, and scalar multiplication, using these new algebraic representations of vectors. As per usual, if you have any questions or thoughts you want to share, please leave those down in the comments section. And don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.